Yes. Hey, hey, hey. Welcome back. Now, let us solve the problem. Merge to BSTs. And again, the question is so straightforward that it is just a single line. So, you are given two BSTs and you have to return elements of the merged BST in the sorted form. So, what does that mean? So, you are given two BSTs. You take all the values of the BSTs, merge them, and return them in the sorted order. And whenever you see BST and sorted, only one thing should go to your mind, and that is in order traversal, because it's a very good trick slash gimmick, what you can tell. And that is that whenever you are given BST and you do an in order traversal of it, you will always get the elements in sorted order. So as soon as you see this question, only one thing should pop into your mind: in order traversal. So how can I apply it? So yeah, first of all, let's get away with the brute force solution. So what is the best thing that can be done? So what we can do is we can actually traverse the entire both the trees in order fashion, and then get all the values. And then what we'll do for those values, we will again what do you call sort them. Like we will add them in a single array and sort them. And again, for that also there are many ways. Like when you're given two sorted arrays, how you will sort. So yeah, we will try to do many of the ways which we can do. Like how many other ways which we can do, we'll try to do that. And so let's get over the best way, which is the brute force way. So what we'll do first, we'll have an in order traversal function. You will have to put self because you're inside a class, and you should give the reference to the in order function, and you will get the root. And what you will do, you'll have an answer variable, and you'll have a stack. And while the stack exists, or you should be able to write this with your eyes closed. So what you will do, while the root exists, you'll just go to the you'll go to the left, but before going to the left, you'll append it to the stack. And what you will do, root is equal to stack.pop. And what you will do, for the answer, you'll append the root dot data, and root is equal to root dot write. Yes. So this is the entire in-order traversal, and by now 90% of the problem is done. So what you will do, you'll just return the answer, and what you will do here, you will just return the sorted form of the in-order traversal of the root one and the in-order traversal of root two. And believe it or not, this is the entire brute force solution. And yeah, it works, and it should work because it is well, it is pretty straightforward on why this works. And I honestly don't know why this is passing in physics, and it would be a lot better if brute force solutions like this did not pass, because yeah, when what some people do is that as soon as they solve the problem anyway, and then they'll just move on to the next problem, not looking at if it was optimal or if it was anything. So what is the time complexity of this? So you're going through all the elements of the two tricks ones. So let's consider the number of nodes in BST1 to be n and number of nodes in BST2 to be n. So we are going through all of them once. So yeah, it is n plus m, and then we're putting it in. First of all, we're putting it in an array of size n plus m, and after getting this, so the case complexity is n plus m. But talking is hard sometimes. So after we get n plus m, what you're doing, you're sorting them. So yeah, so this is the time complexity of this. So can we improve them? Can we improve it? Yeah, we can. I think we can improve it. So what we can do is there is another technique to do when you have two sorted arrays, and let's try to do that first. So what we'll do, we'll have ARR1, which is nothing but the actual array over here, and ARR2, which is nothing but the actual array of this one, root one and root two, and we'll have another answer variable. This time an actual answer variable, and what we'll do, and we'll have two pointers, I comma j, pointing to currently 0 comma 0, and while I is less than length of array 1 and j is less than length of array 2, what we will do, we will compare the elements at array 1 at position I and array 2 position j. Like If ARR1 at the position I is less than ARR2 at the position J, that means that the value at ARR is smaller. And since in order will always give you sorted arrays, G2 will actually be sorted. And after this comparison, we know that ARR at the position I is smaller. So what we'll do, or else what we will do, position J, yeah. But if you just do this and leave, you will get time limit exceeded because you're not updating the pointer, which is very important. And if you tell, okay, my work is done and I'll return answer, you are absolutely wrong. You can't do that because it is not necessary that we have traversed all the values of ARR1 and ARR2. So what we have to do, we have to again go through all the values of ARR1 and all the values of ARR2 from point of I is equal to 0, like from the point where I and J left off, and then we have to append it to the answer. But in Python, we can do that in a shortcut way. Like we can directly extend it ARR1 from I's position to the end, and we'll do the same for J also, like AR2 also, J to the end, and then we can return the answer. This should also theoretically work. Let us see. And yeah, it's working. Let's get submitted. And yeah, so your old type of complexity was n plus m log of n plus m. So now what happened is that this log part got cut out, and it will nothing. It will not be log n plus m. It will be what you call. So you have two arrays, which is again n plus m, and you are traveling them linearly. So again plus n plus m, which is nothing but n plus m. I think I am correct over here. I'm not that sure. Yeah, mainly because we are just going through the entire, what do you call? We are just going through all the elements of the array, and then we are just sorting them and combining them. So I think this is right. Even I'm not that sure about time and space complexity. But well, this is majorly focused on solving the problems. And yeah, this is another way to do it. And now, so what we can do? So rather than getting both the arrays, like both the data in separate arrays and combining them, what we'll do is that we will do a modified in-order search. So let me just remove this. So what we'll do is that we'll do a modified in-order search where we'll keep pointers pointing to both the nodes simultaneously. And while they are in range, like when you, it is like completely similar to this approach itself. Like we'll just do the comparison, and based on the comparison, we will append the next value. So like imagine we are in we are comparing 5 and 2. First, what we have to do is in order, we have to go to the left, complete left. So we will currently be pointing in 2 and 1. So we will compare 2 and 1, and which is smaller, we will remove that node. We will append that to our answer variable, and then we will proceed with the in order transfer of that node. So after appending 2, we'll move back to, after appending 1, we'll move back to 2. And then again, we'll continue the in order. We'll again do comparison, and we see both are equal. So it doesn't matter whatever we put. So imagine I put 3, I put this 2, so it will move to 3 now. And again, the comparison will happen. 2 is smaller than 3. So what will happen is that next, this 2 will be put inside our array, and the pointer will be pointing to this. So like that, we'll do a what you call a stealthy, not stealthy, a clever in order traversal. So let's just do that now. And sad part is that we can't use our above already written in order code. So we will have to write, like it will again be used in this code, but we will, what you tell, first we have to write the modified in order first. So we will have stack 1 to keep track of root 1 elements. We will have stack 2 to keep track of root elements. And then what we'll have, we will have an answer variable to get our answer. And we will do our normal in order traversal. So while root 1 or stack 1 exists, this is how we do normal in order traversal. But what do you have to do? Now we have to keep track of all our nodes. Like we will keep track, not all, but both are nodes. What we'll do, while root 1 or stack 1 or root 2 or stack 2 exists. So what we will do, it does not matter whatever we do. First thing which we always have to do is to go to the extreme left of both the nodes. So while root 1 exists, so we'll do, yeah, we went to the extreme left. And again, we'll do the same thing for root also. And if you think you have gone to the extreme left, you are correct. But in order traversal, you are missing one more thing. To your stack one, you have to append the root value, and we have to do the same for stack two also. And now what you will do? You have went to the extreme left of both the elements, like of both the trees. But by chance, like imagine this tree was null. So what you have to do? You just have to return this entire tree. Or if this entire tree was null, you just have to perform an in-order transfer of this entire tree. In other words, if at any instance of time, if your stack one or stack two becomes empty, that means you have to immediately break out of the loop because we can't proceed with the modified in-order traversal and we have to do normal in-order traversal from there. So, for example, after processing half of these nodes, this will become empty, but we still have the entire. Just imagine that we have this entire subtree to be processed, and since we are going in order traversal only, all the remaining elements will be in sorted order, and we can still perform a normal in order traversal on them. So, what we'll do is stack one or stack two does not exist. So, if stack one does not exist or stack two does not exist, so what we'll do, we'll immediately break out of it. Else, what we'll do? So now what we have to do is to compare the top values of our stack. By now we have assured that our stacks will never be empty. Like in this else condition, our stacks will never be empty. It should be stack two. So our both our stacks will never ever be empty. So we can directly compare the top element without getting what you call accessing an index out of bound error. So what you can do, stack one dot you want to get the stack one at the position minus one dot data. You want to get the stack to at the position minus one dot data, and you want to compare it. The same comparison which we did over there, like if the home, what do you call? Let's go to our submissions and view this code. And if you remember, we are going to do the same comparison over here. If stack one at the position data is less than stack two at the position data, that means that our stack one value is lower. So what we will do, we will process the stack one first. So what does that mean? First, we'll get the root. We'll get the node over there or the root element over there. Root one is equal to stack one dot pop. So you got the what you call the value over here. And now what you will do is that this is the smallest element currently in the entire tree. This is the smallest element. So yeah, you will append that value to your answer array, and then you will proceed with normal in order drive cell, which is root one is equal to root one dot write. So you're proceeding with normal in order traversal depending on if the value was smaller or no, smaller or higher. And we'll do the same thing for the second part also. And we can actually just do this and else case. We'll just get the root 2 is equal to stack 2 dot pop answer dot append stack 2 and root 2 is equal to root 2 dot yeah. And by now what will happen is that uh, yeah, one of these, if both the trees have the same height and same number of nodes in the same places, then both the trees will be processed together simultaneously after exiting this while loop. But what if one of the trees is bigger or smaller than the other tree? That means that your another tree will be left out. So what you have to do? Now you have to perform a normal in-order traversal from your current route, like what you call from your current node. So what you will do? So you can call self dot. Let us see because even I have not done this part. I am just speculating. So you can actually call from root one, I think, and you will get the ARR one, and you can do the same for ARR two also. And what you can do, by now it is guaranteed that only one of these arrays will be full and the other will be definitely empty. It is guaranteed. It is like a given case. So there's no need for us to be scared of which should be appended first. So what we can do, we can directly go to our answer and we can extend the entire thing. This is because again I'm repeating, it is guaranteed by this point that only one of these two calls will return the answer. Yeah. And then I think we can do compile and run. This should work. Let us see. Okay, and let's why is it not working? Uh, let's just print it out. most root 2. Let's just comment this out and let's do compile it. Okay. Um, oh, I forgot to print it. Okay, I got it. Because we theoretically can't do this because we have to pass our stack also. So what you have to do, you have to pass our stack also, and we will have to remove this. And then because our stack contains our what you call unprocessed elements, I forgot to do that. Yeah, I mean I have to do that over here, and I can just uh, copy this entire part and paste it over here. I don't know why I forgot to take this into consideration. Our stack still contains. See, one of these stacks will still not be empty. One of them will be empty, but one of them will not be empty and will still contain unprocessed elements. And yeah, now it's working. And let's submit and check it out. Yeah, as you see, this solution also works. And yeah, again, like I showed like three ways to do it. Two ways are of brute force and brute force optimized, and a really good solution also. And yeah, that was this part was pretty ingenious, I think. Just putting it like using our pre-written in order traversal function to go through our, what do you call stack and process our nodes. And yeah, that's all for it. And if you watched till now, thank you for watching. And granular DSA, I know you can do it. And yeah, that's all. Goodbye.